Welcome, listeners. So, again, we have gathered here to discuss on the next topic on the series of lectures on fundamentals of geology. And I'm Dr. Shandy Banerjee, a faculty member in the Department of Geology, Banaras Hindu University, Varanasi. So, the next topic that should be discussed after the formation of minerals, followed by the classification of minerals. Now, obviously, whenever we are talking about minerals, we also need to identify them. There are various ways to identify minerals, but we'll try to look into a specific way in more detail, but we'll be also discussing a few techniques before going into the main uh, technique or main determination technique for minerals when you will be, as a geologist, when you will be looking into rocks and minerals in field. So, obviously, the first way to determine the mineral, that what is the name of a mineral or which mineral you are dealing with, always remember that there are two things that needs to be ascertained. The first thing is obviously the composition of the mineral, and secondly also the structure or the crystal structure of the mineral. And we have also discussed about the crystal structure a particular mineral possess when we discussed about your formation and classification of minerals, as well as we looked into when we discussed about crystallography, matlab, a few lectures from this one. In that one we discussed about that how your crystal geometry can be also used to determine the crystal structure of a particular mineral. So, apart from the other ways, the first technique to determine a mineral is by the elemental analysis of the mineral. So, definitely a mineral, like we have seen in case of formation or in during our discussion on classification of minerals, we have seen that a mineral is composed of certain crystals, and the crystal structure also, apart from its composition, the crystal structure is also very important. So, obviously, like we discussed about that minerals are substances that have a definite arrangement of atoms and molecules, and also there are several elements that are the main constituent of a mineral. So, to identify those elements, there are some high-end instruments, or you can say sophisticated instruments like LAIC PMS or EPMA, electron probe microanalyzer, through which you can determine the elemental content of any mineral. But the problem is that these sophisticated instruments, they are obviously costly, as well as they need skilled workers to deal or to run these sophisticated instruments. Apart from that, there are several uses of these instruments, like they are used for the understanding of properties and behavior of minerals, as well as apart from the identification of mineral species, they are crucial also in fields of material science and solid state chemistry as well. So, these instruments, though they are not very common in different institutes or universities, because of their, mainly because of their cost, because they come in several crores of rupees. So, in that case, and also you need trained and skilled personnel who can help you to run certain analysis to determine the elements present in a mineral. Apart from that, the other instrument that we have discussed a bit when we discussed about X-ray crystallography, that using X-ray diffraction on the concept based on the equation that has been provided by Lawrence Bragg in early 1950 in at that time. So, and he also proposed the equation of n lambda is equal to 2d sin theta. So, based on that concept and that idea and equation, what we do, we generally take the powdered form of a particular mineral and we try to analyze that under your X-ray, and for this also you need obviously an X-ray diffraction instrument, and also you need trained and skilled personnel who can obviously run or have an idea to how to use this idea of diffraction to analyze or ascertain the mineralogy of a rock if you are dealing with the powder form of a rock, or if you are dealing with means you can say the powder form of a mineral, you can also essentially determine the composition as well as the structure of that mineral. The other applications of XRD includes pharmaceutical industry, forensics and archaeology as well. So what we do in X-ray diffraction is nothing but we inject or we simply use X-ray as an incident ray on the crystal faces or the faces of a mineral, and based on the diffraction that we get at some detector, like this simple diagram shows you that here your X-ray is are being generated and they are getting reflected from the surface of a sample, be it a single mineral or be several minerals, but at a time your X-ray will obviously get reflected from the surface of a particular mineral, and they are gathered at a detector. Based on that, your diffractograms get generated like this, and based on the intensity of this you can also determine the angle, that is the theta angle, in the equation of n lambda 2d sin theta. Apart from that, you can also have the intensity of these high peaks, and you can say that, for example, this particular diffractogram is showing you the content of quartz, albite and diopside. So based on the presence or based on the, you can say, the size or the intensity of the peaks, you can also comment on the relative content of these individual minerals in that particular powder sample that you are using under this instrument. Then there is another technique to identify minerals is by the application of an optical microscope. But before looking into an optical microscope, what you need is that you need to develop thin sections of a mineral or of a rock to see through in an optical microscope. And how it is done, obviously, if I want to prepare a thin section of a particular mineral or a particular rock, to be specific, in that case what we do, we generally cut a chip or a slice from that rock and we grind it till the, after cutting the slice, we generally mount it on a glass slide by applying some adhesive, some glue, and then we grind it and polish it to such a level, specifically it is about 30 micron, but literally it means after the preparation of thin section, it happens in such a way after the grinding and polishing that literally light can pass through your thin section. It is so thin that light can definitely pass through that slide or thin section you are preparing. So this is an example of a thin section. You can see that obviously you can see beyond also this very thin slice of rock that is mounted on this glass slide. So you can see beyond this glass slide as well. So based on now, after preparation of this thin section, what we do, we generally put it under an optical microscope through which your light is emitting or it is passing through your thin section, and in that case you can identify based on various optical properties. Your different mineral shows different color, it shows different, you can say, structures that are present within the mineral. For example, cleavage, we'll be discussing about cleavage in a bit, but we can see cleavage, we can see fractures, we can see also some inclusion of some other mineral within a particular mineral, as well as we can also look at the interference figure of different minerals to finally ascertain that in which crystal system, like we discussed about crystal system in our earlier lectures, in which crystal system your mineral belong. So based on this idea, we generally use optical microscopy, and that is also a very useful way of determination of your mineralogy of a rock or the character of different mineral. But The problem is that be it your XRD instrument, be it your EPM instrument, or even be it your optical microscope, you can't take it along with you during your field. And obviously, to see rocks, you have to go out from the what we call means industrial or the infrastructural settlement of any city. You have to go out in the field somewhere, relatively small virgin areas, or sometimes in the mountains, or sometimes in the different cratons. So for that you need to go out to see rocks. So at that time when you are in the field, you can't really determine, unless you have some prior theoretical knowledge in your mind or some theoretical background in your mind, that how to determine or how to recognize a mineral that you can directly see within a rock in the field. So you can't take an instrument as heavy as your XRD, or you can't really take up any, or you can't build a laboratory that is having sophisticated instruments like EPMA, and you can't really set up that in your field so that you can take some sample and directly analyze. So for that also, if I talk about the optical microscope, still it is not possible, because to look into the optical microscope, first you need to prepare a thin section of a mineral or a rock so that you can study it under the optical microscope, but that is not directly possible in the field. And as we all know that the role of a geologist is always start with the observation that you do during your field work, when you are really looking at naturally occurring minerals and rocks. So the most useful way of determining your rocks or minerals in case of field, we'll be talking about that. But before that, one thing that I would like to also mention, in case of microscopic identification using thin section, you can do your textural analysis, which means that your thin section allow the examination of arrangement, size and shape of minerals, as well as the interrelationship between the minerals in a particular rock. Like this one, you can here see some overgrowth of quartz within feldspar, which is also referred to as your myrmekite texture. Then you can do also some structural analysis, like for identifying features like cleavage, fractures. I was referring to cleavage, fractures. We will also look into detail into cleavage and fractures, grain boundaries, and even crystallographic orientation, like we discussed in crystallography. So you can also look at typical, this is an example of a typical pseudomorph structure. Inside there is a mineral called garnet, and it is circumferenced by a mineral that is chloride, and there is a reaction that has led to the formation of this kind of a very beautiful hexagonal structure, with garnet sitting at the central position of this structure, and chloride that are circumferencing the garnet, and it is mimicking the shape of the garnet as well. Then also you can determine, like we discussed, you need to have the idea of the composition, also you need to have an idea about the structure. So the composition definitely means it is the mineralogy or the minerals that are contained or that are present in a rock. So for example, again if I look at a typical granite under microscope like this, under cross polarized light, in that case you can see that there is abundance of quartz here, orthoclase, plagioclase, as well as biotite. So this is a typical example of a granite rock. We have discussed about your granite and basalt that make up the crust of the earth. Now I'll say not the easiest, but it is obviously the most feasible way to determine in the name of a mineral, because there are more than 3000 minerals that are present on earth, and they means make up several rocks. So the problem is that you can't really remember all the mineral names or their characters. But like we discussed during when we discussed our classification of minerals, we have seen that there are a few rock forming minerals, and the number of the rock forming minerals generally speaking is finite, because we have seen that there are a few ferromagnesium silicate minerals that are present in rock, as well as there are non-ferromagnesium silicate minerals that are present in rocks. So, in totality, if I look at the silicate minerals, there are 9 silicate minerals that needs to be identified, and for that we will be discussing a few characters, as well as there are a few non-silicate minerals, like for example halite, then you have your hematite, then you have some other sulfide minerals like chalcopyrite, pyrite, like that. So, if I now go into the broad discussion of your identification of mineral in hand specimen, then we will try to look at the main characters that a mineral possess, as well as we will be discussing on the later part of this lecture only, we will be also discussing a few diagnostic properties by recognizing which you can also identify the mineral that you are looking at. But we will be mainly discussing the characters of the rock forming minerals. As we know that these 9 rock forming minerals is mainly controlling the, you can say, by volume 90% of volume of the rocks that are present on earth, and apart from that the non-silicate minerals, they are contributing about 10% of all the rocks that are present on earth. So, your now when you are in field, if you are looking at some rocks, you need to also identify again the composition of the rock, and that can be only done if you can recognize the minerals that are constituting the rock, or the minerals that are present in the rock. So, you need to have a clear idea about the mineralogy of a rock that also reflects the composition of a rock. So, here are the few visual characteristics that play a crucial role in the hand specimen identification of minerals, starting with the color, the hue of mineral or rock, obviously luster, the way the light gets reflected from the surface of a mineral. There could be several types of luster: metallic, vitreous, dull, silky, pearly. There are several types of luster. Then definitely texture, that refers to the feel or appearance of the surface as smooth, rough or granular. You can also look at the cleavage, the way a mineral breaks finally along planes of weakness. And also you have fractures that are generally associated with cleavage, but it is not essential that always a mineral will possess both. A mineral might possess a cleavage, no fracture, but also there are minerals which might possess fracture with no cleavage in it. So, cleavages are simply immense. You can think of, when we discussed about the formation of minerals, we talked about van der Waals forces that are keeping some sheets of minerals together in space. So, if I say that in a mineral that you have a, for example, sheet like mineral that is having some covalent bond within the sheet, but across the sheet they are associated with the van der Waals forces. So, your van der Waals forces, as we know, that is the weakest kind of force that is present within in the different types of bonds, or it is the weakest bond. So, the mineral will tend to break, or you can also, by simply peeling it apart or by hammering it, you can also break minerals along those zones of weak bonding that are represented by van der Waals forces. But in case of fracture, it is not related directly with the bonding that is present on the mineral. Fracture is simply, so here I can also say that cleavage is governed by the kind of bonding a mineral possesses, but fracture is not governed by any kind of bonding that is present in a mineral. Then you also have hardness, the resistance to scratching, that is also measured on Mohs scale, we will be looking into that. And you also have the crystal form, the shape in which a mineral naturally occurs, as we have also seen when we discussed about the crystallography. So, the other characteristic that might include are streak, that is the color of the powdered form of a mineral, and sometimes streak it also becomes diagnostic for a mineral, transparency, magnetism, reaction to acid as well, and sometimes as well your specific gravity is also important. So, now if I list the physical properties one by one, I will start with color, streak, hardness, cleavage, fracture, crystal form, luster, specific gravity, magnetism, reaction to acid, fluorescence, and also electrical conductivity. So now if I start with the first character of any mineral, we look at the color of a mineral, the hue or shade of a mineral, which also can vary widely, but sometimes for a particular set of minerals, color can also become diagnostic, but it is generally not a diagnostic feature. But in case of azurite mineral, you can say very beautiful blue color, it is exhibiting a very beautiful blue color. So your azurite can be identified with this kind of a blue color it possesses. But you can now see a mineral that is fluorite. Fluorite of two different colors are present alongside like this. So remember that color is usually not a diagnostic property of a mineral, but sometimes for a few minerals it could become a diagnostic one. Then also the streak, the color of the powder form of a mineral when scratched against a hard or rough surface. For this we generally use a plate that is streak plate, which is made up of china clay, and it is having a hardness, according to the Mohs scale of hardness, it is having a hardness of around 6.5. So the minerals which are having hardness less than that can be powdered on the surface or by simply scratching the mineral on the surface of a streak plate. And like that, based on the color of the powder form of the mineral, you can also determine the mineralogy. It's a small plate, you can also carry it in your pocket when you are in the field, and you can directly rub your rock or mineral on the streak plate and you can identify the color of the streak. And based on in some cases it is very characteristic. For example, if you are looking at hematite, hematite will always give you a cherry red kind of a streak. Then comes your hardness, the resistance of a mineral to scratching or abrasion, typically measured on the Mohs scale, and that has been designed by Frederick Mohs. So if I now take this scale, remember this is not an absolute scale, this is actually a relative scale with different minerals in that scale, starting with the relative hardness of 1, that is represented by talc. Then you have second one gypsum, third is your calcite, fourth fluorite, fifth your apatite, sixth is your feldspar, 7 is your quartz, 8th is your topaz, 9 is your corundum, and obviously the hardest one, that is your diamond. So if I now also see this ranking with in reference to the absolute scale, you can see that diamond is way above all the minerals that are present in that naturally occurring any mineral. Diamond is obviously the hardest one. So here also there are some ways to identify the hardness. You can even start with your fingernail, which is having a relative hardness of according to the Mohs scale, it is having a hardness of 2.5. So any mineral which is getting scratched through your fingernail obviously has a hardness less than that of the fingernail. Simply you can apply copper coins also to scratch minerals. If it is getting scratched, you can also say that the hardness of the mineral is less than that of the copper coin. Similarly, you can take a hardness of 5.5, that is generally your steel knife, and also your streak plate, that is your 6.5. So a mineral which is giving you a streak or some color of the streak, it could be white, it could be black, it could be any color in between that, then obviously you can say the hardness of the mineral is less than that of 6.5 or it is less than that of streak plate. But if it is not scratching the streak plate, or the streak plate itself is getting scratched, or itself it is giving some white powders, then also you can comment definitely the hardness of the mineral is greater than that of the streak plate. So there is a chart, you can look at this in detail when you get time, when you will see there are several minerals which are placed in this relative Mohs scale between your 0 to 10. Then you have the character of cleavage and fracture. So you can see, first we will talk about fracture, which is not related to the bonding of mineral. In that case, a very characteristic type of fracture, you can say conchoidal, that is exhibited by a mineral that is obsidian, which has a similar composition of that of quartz. You can also look at quartz. If I look at quartz like this, then you can see that your individual, there are fracture planes that are present in the quartz. But if I now look at the internal structure of a quartz, you will not see any kind of cleavage that is present in here. So we'll show you also some examples of cleavage, but in this you can say that there are different fractures, some are irregular as well, and there are some fractures, if I look very closely, within this crystal there are some, you can say, subcircular kind of fractures that are present, and in this you can also say this kind of fracture is termed as conchoidal fracture. So in case of you can also compare conchoidal fracture when you simply fracture a transparent glass. So glass also have a tendency to get fractured in this kind of a pattern that will give you conchoidal fracture, and be it your obsidian, be it your quartz, both have similar composition, obviously SiO2, so both of them will give you fracture of your this conchoidal pattern. Then talking about your cleavage, obviously refers to how a mineral breaks along flat surfaces. And why flat surfaces? Because these surfaces are nothing but the surfaces or planes of weakness. Weakness means where your bonding is, the strength of the bonding is minimum, like we were referring to the van der Waals forces. For example, here if I look at a muscovite, again if I can demonstrate, this is a muscovite mineral, you can see, and if I try to peel this off, you can see here that I can simply peel this sheet apart from the rest of the mineral. So I can simply try to peel, if I peel it apart, then itself the small slice is not breaking into parts. What I am doing, I am peeling it apart from the rest of the slices that are making up this kind of a mineral. So if I am peeling it apart, that means individual sheet that is getting separated from the rest of the mineral have, if I say the individual slices that is making up this muscovite, they have a strong covalent bond within them. But if I compare among the slices that are making up this mineral, that is muscovite, then there is van der Waals forces that are present across this mineral. So I can have these planes of weakness that are parallel to one another, obviously, and they act kind of a base like a structure with lines like this. So I can say these are basal cleavages that are present in muscovite. So I can also look at, for example, feldspar. When you can have some step like geometry, there is a feldspar, you can say there is step like geometry. So you can simply assume your staircase geometry. So you have a horizontal plane, you have a vertical plane, again you have a horizontal plane, again you have a vertical plane. That what makes up a staircase geometry. So here also, if I am looking at a staircase geometry like this, I can say at least there are two planes which are making up this kind of a staircase geometry. So you can say that there are planes of weakness going like this, there are planes of weakness going like this. So that how also cleavage forms in case of a feldspar mineral. Then also it is similar in case if I am looking at a halite. Now to have a small discussion on halite, if I look at the rock salt that we generally use. So if I want to powder the rock salt, or if I simply try to break it apart, also the small particles that are now being given up by the your halite or your rock salt, it also comes in cubic structure. So why it is so? If it is the overall structure as well as the tiny particles that are breaking apart from a lump of halite, you can say these individual particles will also possess a cubic kind of a structure. It is nothing but due to the presence of now 3 cleavage planes. So now if you have 3 cleavage planes that you can think of, then you have this kind of a staircase geometry with horizontal planes, vertical planes. Again you can say sidewise a vertical plane is also present. So now if I think about that, you have planes going horizontally, you have planes going vertically like this, also vertically like this. So now if I break it apart, then the tiny particles that make up your halite lump is also breaking up into small cubes. So that also gives you an idea that a mineral definitely possesses your 3 cleavages. Again if I look at a different example like that of calcite. Here you can, though it occurs in a rhombic form, you can see at the rhombic form of calcite. Here you have planes like this, and like this. All they are not exactly horizontal or vertical in nature, but they are forming a rhombic shape. You can get stair like structure on 2 or 3 faces of the calcite mineral. So here I can also say that this mineral possesses at least 3 cleavage planes. So based on this idea, we can determine the presence of cleavage in a mineral. So these are the different types. Again, the basalt one, the prismatic one, if there are 2 sets like I was discussing about when we are dealing with orthoclase or feldspar. So in that case, you have this prismatic cleavages. Then you also have your 3 sets when you are means dealing with your halide, or you can say in that case it will be your cubic cleavage in case of halide. In case of calcite, what it is giving you an overall rhombic shape. So the type of cleavage is rhombic here in nature. Again 3 sets, but in a rhombic manner. So that's why it is giving you a rhombic form. So here I would like to stop here first, then again we will discuss in the second part of this lecture about the other properties as well. But here before I conclude the first part of this hand specimen identification, I will say that always remember, if I simply look at the first few physical properties, then starting with the color could become a diagnostic feature for a few minerals. For rest it is not diagnostic. Same as that of streak could also become a diagnostic feature of a mineral, but again there are several minerals which also show same kind of color of the powdered form of that mineral. Then you have hardness. Hardness is definitely a diagnostic property, because generally there is a difference between the hardness of 2 minerals, be it at decimals point even. You can differentiate between the hardness, but when we are looking at the hand specimen, generally we determine hardness, or we assign hardness based on in relative with respect to your finger nail, be it your knife, be it your streak plate. We generally deal in that way. And also by comparing 2 minerals having a greater hardness, having a softer hardness, you can also have a hardness kit with minerals having hardness from 1 to 10, and you can rub that mineral with the other mineral which is unknown. You have a known mineral with, for example, known hardness of 7, and you are rubbing into your unknown mineral. So if it is getting scratched, definitely the unknown mineral is having a hardness less than that of 7, and if it is not getting scratched and it is the other way around, the unknown one is getting or the unknown one is scratching the known one, then obviously the hardness is greater than that of 7. And also you will have looked into cleavage and fracture. So cleavage is strictly governed by the bonding that is present in the mineral, but fracture is not a character of the internal atomic bonding that is present in a mineral. So in the second part of this lecture, we will be also discussing about the other properties. So we will continue with the hand specimen identification of different naturally occurring rock forming minerals. Thank you.